We're going to take a look at a full regression process. So starting out with considering the very early assumptions, going through every single assumption with a sample write-up, all the way through performing the regression, and then doing your final write-up. And so when we're talking about a regression, remember the keyword is a prediction. So we are looking to see if something predicts something else. It's not necessarily a cause and effect, but does it predict? So in order for them to predict, both of your variables must be continuous. None of them can be categories, basically. So you can't look at ethnicity, you can't look at letter grade, you would have to look at a number grade, age, weight, hours studied each week, income. They have to be actual measurable scale data that you are inputting into SPSS. In your assumption section, you will need to directly state the dependent variable, whatever you think it is. So in this situation, we're thinking that the grade in high school predicts the math achievement score. So the thing that's being predicted is the dependent variable. And you need to directly state it was measured on a continuous scale, meeting the assumption required for a linear regression. And you must have a citation from a mathematics textbook, your IBM SPSS book, or something else showing that you are citing that information. The variable that is doing the prediction would be your independent variable. So here, again, we're saying that grades in high school predict math achievement, so therefore my grades in high school are my independent variable. And again, in my assumptions, I'm just going to have a one-sentence write-up that does that, that cites the textbook. So those are the simplest predictions that we have. The next one is that we're assuming linearity. Now, if it's not linear, we can do different types of regressions, but the way that we would do this is we would create a scatter plot. So we are going to create a scatter plot that graphs the two variables that we're looking at, and we're going to see if the dots form a line or not. So I'm going to go to the appendix, which is where I have the information on making the scatter plot with. So notice I'm not in the linear regression menu. I'm actually going to Graphs, then into Chart Builder. Once I get into Chart Builder, you should have something like this screen. What we're going to want to do in this screen is in the bottom left, you're going to want to select Scattered Dot, and you're going to click and drag it over to this window. So over here, you're going to click one of the scatter dots after you select it, and you're going to bring it over. Which one do you want? You want the simple one, the upper left one. Don't pick any of the other ones. Then you're going to look at that graph and see if it forms a line. Typically what will happen is it's going to form a line exactly along where my mouse is tracing. So you're going to see dots clustered up on this diagonal line. If you don't, it's not linear. So here, for instance, we're seeing not quite a linear relationship, but something that could kind of be close to it. And you see these arrows. So these arrows are saying you're going to take each variable and you're going to drag it into the window. Then we're going to click OK. So what pre-populates here is not the final scatter plot. This is just kind of a preview window. So you want to click OK so that the actual scatter plot comes up. If it is not linear, you need to talk to your dissertation committee people because it is possible you'll need to do a transformation on the data. Or it might be that it's okay that it's not linear because what you're doing is robust enough. So that's a conversation to be had if it violates the linear assumption. What you're going to need to do is insert the scatter plot you just made, and then you're just going to do a write-up. The scatter plot was generated to look at the relationship between your independent and your dependent variables. The scatter plot either did or did not indicate a linear relationship, satisfying that assumption. So whether it breaks the assumption or not, you still have to say it. You still have to put the scatter plot into your write-up. Now the next one is no significant outliers. We can have some kind of out there figures at times, and it's okay. But other times, if they're extreme, they're going to influence the test entirely too much. And so we have to take action against that. So what we're going to do, and there's a lot of ways to check for outliers, the one that I recommend is creating a box and whisker plot. So you'll see in the write-up, I've got insert that image, and again, in the appendix, I have the instructions on how to create the box and whisker plot. And it's a pretty simple process. So you're going to go to Analyze, you're going to go to Descriptive Statistics, you're going to select Explore, you're going to move over whatever you are looking to plot, all of those scale variables. So in this case, they have 5 because this is actually one that they're conducting for a multiple regression. Since you're doing a linear regression, you really shouldn't have more than 2. You're going to click Statistics, you're going to check off Outliers, you're going to click Plots, and you're going to select Dependents Together. Then you're going to select Options, Exclude Cases Pairwise. So this is what we want to have selected. Then we're going to go ahead and click OK, and it's going to create our box and whisker plot. In a box and whisker plot, if there are any dots that are above or below the whiskers, those are extreme outliers. Okay? So when we're talking about that box and whisker, if there are any dots in the plot that are beyond either above the whisker line or below it, those are significant. And so if there are outliers, you have 3 options. You can see, did you mistakenly enter something, which actually happens a whole lot? Was there some type of measurement error? Maybe some equipment was faulty, maybe a test score got messed up in the computer, or is it actually just an unusual value? Depending on what category it falls in, you'll want to take different actions and adjust your write-ups. So for instance, here, if I did find a genuine outlier and I wanted to keep it, this is a sample write-up that you would add in below the image and below your statement. And notice we're consistently having these citations for each area of fact. Now, what's interesting is assumption 5 is not actually something we can confirm in SPSS. In the education field, observations are generally independent. What that means is my high school grade is not done at the same time as my math achievement score. They're happening at different points in time, okay? One does not depend on the other. If I get an A in high school grades, I don't automatically get something in a math achievement score. Typically, we just need to articulate this correctly. Observations were collected independently, and no repeated measures were there. So nothing like where I was test and retest, pre-post test. Those need to be true. Now, the next couple of assumptions, what's interesting is we can't actually check them until we do the linear regression. So as a part of running the linear regression, you're going to wind up with this plot that's created to check homoscedasticity. Sometimes I have to think real hard about that. So we're going to create an image as we do the linear regression that's going to give us a plot. We want the plot to have no pattern. We want it to look like this. We don't want it to look like this. It just should look like random dots. Then you would put your image here of what you generate after you do the linear regression, and you would insert your write-up. The same thing is true for the normality of residuals. You can't do this until after the linear regression is run. So it's really important that you're waiting to do this until you run the linear regression, because you're not going to find it in the menus if you're just looking for this. You're going to do the image that it gives you, and you're going to give the statement. And what we are looking for is in the histogram that it generates, we want it to be a normal distribution, meaning the highest point should be in the middle and they should gradually get lower. It needs to be approximately normal. It's okay if it's not perfect. See, these bars are still taller. It's okay, but it needs to at least approximately look like that. Once you have done the write-up for this, you're going to have kind of a final bring it all together and say, all these assumptions were evaluated and satisfied, or maybe 5 out of 6 were evaluated and satisfied. So this sentence is going to change based on if any of the assumptions got violated. And it's just kind of recapping everything as one. Once you've got all that done, you're ready to conduct the regression, remembering, though, that assumptions 7 and 8 happen as you're doing the regression. So basically, you would want to do 1 through all the others. Then you're going to conduct the regression by going to Analyze, Regression, Linear. Once you get into that window, you're going to put the variable that you think will be predicted into dependent, the variable that you think will do the predicting into the independent, just like this image right here. And then you're going to click the statistics button, which is right here. So I'm going to click statistics. I'm going to make sure that I have estimates checked off, the model check off, and then I'm going to also make sure that I'm checking off all of these final things. And I will select Continue, which brings me to this box. Inside of this box, I'm going to transfer zResID and zPred. So whatever your variables are, you're going to transfer them. So in this case, these are the variables in the example screenshots that I did, but this would be your variables. So you're going to move them in. Then you're going to select histogram, you're going to select normal probability plot, and you're going to select Continue, which is going to bring you back to that linear regression box, and you click OK. So this is what's generating those last 2 assumptions, is this box right here. Then you're going to get your outputs. So you're going to get a variables entered and removed table, where you're going to see that independent variable. It's going to highlight your dependent variable, and it's going to tell you if there were any removed values. This table is not incredibly helpful. It's just more of a level set piece here. The next table is the model summary table. In this table, you're given an R value, which is going to be the R between, or the relationship between, grades and math achievement. This is the same one that's also found in figure 8.3 in the text. So this is what's important right here. And then you get this table, and even though it's calling it an ANOVA table, it's actually not really a typical ANOVA. Instead, it's looking, does the variable significantly predict? So it's possible it could predict something, but it may not significantly predict it, and that's why it's having that ANOVA designation. And so if you are looking at this, I would report my capital F, 1 and 73, which are coming from the regression and the residual lines, equals, then I'm going to select the F value of 24.868. I notice that P is less than 0.001. I know that from earlier in this table, my R is a 0.5. And that R is really measuring my effect size. And we're going to see that when we get to the write-up. So as a recap, you need to know your 1 and your 73, your degrees of freedom. You need to know the F value that goes with it. You need to look at the sig area, and then you need to look at the R value. In the coefficients table, the constant is going to be the y-intercept of the predicting equation. So I can generate a predicting equation from this. Then I have the regression coefficient, which is what goes in here. So essentially, this makes an equation of 2.142x plus 0.397. So if I plugged in, let's say, an 87-point grade for high school, into that equation, and I did 2.142 times 87 plus 0.397, and I put that in there, I should be able to get very close to the math achievement score. And that is how linear regression predicts. It creates this equation that we should be able to plug in the value of a grade and get out the math achievement prediction. And it should be close in accuracy if it is significant. So that's going to be key. You should also notice that this value is not the same thing as that 0.504 that's located here. That's going to be different. Now, when I start looking at these outputs, all I did here was I kind of gave you, looking at that output, what does it actually mean? So that R value in this table right here is actually telling me the correlation between high school grades and math achievement. So what do I mean by correlation? The relationship. So 0.5 is moderate, 0.75 is strong, less than 0.5 is generally found to be weak. So here we have a moderate relationship and it's positive. So I would say that 0.504 is a moderate positive relationship. Then I have my R squared value. And what that R squared value, which is up here right next to it, what this is that 25.4% of the differences in math achievement are explained by the high school grades. So this R figure tells us the percent of the variable that is explained by the predicting variable. Then I have my adjusted R squared, which basically just accounts for the number of predictors and can give a slightly more precise answer. We have only one predictor is used, and then when I get to that ANOVA table, remember I'm looking at the significance value. So if you're looking at that significance value and it is less than 0.001, it is statistically significant. If it is greater than 0.05, it is not statistically significant. And which again, the correct terminology is that it significantly predicts or it does not significantly predict. So we really need to have that significantly there. Now, if I'm in that coefficients table, that 2.142 right here, that 2.142 is the slope of the regression line. It is the number that comes in front of x when I'm forming the equation for the prediction. The constant is the y-intercept. So again, if I have these values, my equation would be y equals 2.142x plus 0.397. This is my prediction equation. If I plug things into my prediction equation, I can get things out of it. So if I put in a test score, I can get, if I put in a grade in high school, I can get out a test score. That is what that coefficients table is. A couple of important notes here is that high school would explain 24% of the variation, and that's coming from that value, that R squared. So either 24 if you want to use the adjusted one, or 25 if you want to use the R squared. I tend to always use the adjusted R squared because it's more precise. So 24% of the variation accounts for it. Now, if 24% of it is accounted for by that variable, it's interesting because there's still 76% being explained by something else. We don't know what it is. When you're doing your interpretation in your chapter 5, you get to hypothesize what those other things might be, and you could suggest and say maybe a multiple regression is the next logical study that is done. So that's really kind of the important part. And so this guide I have here also just reinforces how you would read the table that I just walked through. So I'm not going to walk through it again. Here is the APA template for how you would fill in the write-up. And so if you're looking for how to fill in the write-up, this walks you through it. So if I'm looking for my predictor variable, that is my independent variable. If I'm looking for my outcome variable, that is my dependent variable. If I'm looking for the statistically significant, I'm looking at that p-value from that ANOVA table. If this p-value over here is significant, then it significantly predicts. If it is not significant because it's greater than 0.05, it does not significantly predict. So basically, this is giving you kind of where to find the information to plug into the APA template write-up. Once you have completed that APA template write-up, and I gave you an example here so you can look at how I filled mine in, and you'll be able to validate and say, that makes sense. And then you can start making your interpretation. So what is that other 76% of variation that's not there? What is that other amount of information that's not there? So there's a lot of things that you can now do with this and that you can now put together in your final report. So this is walking through a linear regression from start to finish, looking at the assumptions, looking at the different plots that I get, and then doing the final write-up for the linear regression to know if it significantly predicts anything.